Ladies and gentlemen, when it is 3 o'clock in Netherlands, we are all over the world today to talk about glass processing. Welcome everyone to the brightest, shiniest, transparent glass meeting in your lives. Welcome to the Epic Online Technology Meeting on glass processing.
We don't see the videos?
Glass panes as easy to scratch and easy to shatter. But when Steve Jobs was developing the iPhone, they called Corning. The result was Gorilla Glass, which is very difficult to scratch. The latest version, Gorilla Victus, takes things to a new level. And that was just the beginning. The future is smart glass. With the smart glass, you can collect information and display it where it's needed. All the new upcoming applications of glass have something in common. They have to be perfectly smooth, scratch-proof, and with added functionality to detect your fingerprints or send something through it. So we need to manipulate glass. Many industrial applications require joining glass to other materials like silicon, and that's where the specialized talents of EPIC members come in. Take workshop of Photonics in Lithuania. They use ultra-fast femtosecond and picosecond lasers combined with extremely accurate optics to cut Corning glass. The high-end watch industry has chosen sapphire crystal as the material of choice. Sapphire can only be scratched by diamond, but producing and processing synthetic sapphires needs extremely accurate methods. On October 12th, our Zoom room will bring together new and traditional end users of glass to discuss changing trends and new opportunities. I want leading companies in different application fields like Bosch, Swarovski, Huawei, Audi to interact with glass manufacturers like Corning or SCHOTT and find opportunities for photonic companies including Forget, Workshop of Photonics, OPTOMAN, Asphericon, Coherent or Ekspla. So let's explore business during our in-depth discussion on Monday, October 12th at precisely 3 p.m. Central European Time. And this time we promise not to scratch the surface. That's it. Thank you very much for joining this EPIC meeting. It is quite an amazing week for EPIC. I don't know if you are aware of something that happened last week. Perhaps not important for you, but it's very, very important for all of us. Last week, EPIC became the largest photonic association on this very planet. EPIC, with 620 members, is now the largest association in photonics in the world. So I would like to say thank you so much from the bottom of my heart and also on behalf of all my team for making this amazing dream come true. It's not about being the largest, it's about knowing each of you individually, and that's never gonna finish. We still want to know each member individually and know what are your preferred partners, suppliers, and customers, and what is your preferred future, and which companies you need to get there. But I don't know if it's important for you, but it's important for me. We are now the largest photonic association in planet Earth. Thank you very, very, very much. But also I would like to say that we continue with the season 2 of the EPIC Online Technology Meetings. Today, 12 October, we talk about laser glass processing. Next Monday, do not miss this one. Next Monday, we talk about advanced and additive metal manufacturing, 3D printing of metal, and actually high-end cutting, welding, drilling of metal, steel especially. We're going to talk to end users about this. Do not miss this one. But we're also going to have events on LiDAR, on Li-Fi, for those interested in 3D sensing. If you want to enter the medical market, if you're interested in the food and beverage industry, we are touching every single topic that makes a difference with Photonics, with the rest of the 620 members. Please do not miss our meetings. If you want to participate in any of them, register online or simply send me an email and I'll make sure sure you get there. I also would like to say that for those of you who don't know Epic, you don't belong to our 620, I cannot stop saying that, or 620 companies. So remember that we organize events, we provide access to the network, we give you access to investment. We had the biggest website in the world to find a job in Photonics, jobsinphotonics.com, and we also have a long list of market reports, long list of market reports, 17,000 view graphs that all the Epic members have free access to. But most important, we do at Epic is connect companies, and I love doing that. Today we connect companies in laser glass processing. First of all, I would like to acknowledge and thank the companies who made this meeting possible, and those are our sponsors today. And we do have a lot because, Francesca, this is a very hot topic. I'm going to start. Forget, if you're looking for a company in the system integration, system engineering, or service processing for surface extraction, laser cleaning, anything that has to do with laser industry, talk to my colleagues at Forget. They are the key company to help you build a system or actually make a process for any laser-based manufacturing service. OPTOMAN, all the way from Lithuania. Whenever you're looking for IBS coating for optics that work very well with high power and also high speed rate and high fluence solutions, you have to talk to OPTOMAN. They have fantastic IBS coating service. You're looking for aspherical or freeform optics, you have to go to the capital of optics in Jena, and you have to stop by Asphericon. Asphericon is the kind of company that has made a paradigm shift in the typical values and accuracy for freeform aspherical optics. But if you have a laser system and what you want is to characterize, to measure it, to actually make testing or even measure the power of your laser, you go to Italy and you go to Laserpoint, the best characterization solutions for characterizing laser systems they get from Laserpoint. If you're looking for a partner to help you make a process on glass or any material processing service, you go to Lithuania and you go to workshop of Photonics, a key company that has made a huge difference in Epic, bringing laser technologies on different markets all the way to the consumer market. And you stay in Lithuania and you're looking for a short pulse, high quality laser, you go to the femtosecond and high speed ultra-fast lasers from Ekspla, all the way from imaging, spectroscopy, and microscopy, any solution, Ekspla has the right solution. And finally, in Poland, a company that had made a huge difference in the ecosystem, a company that when I met them last year at Laser World Photonics, I fell in love with, Fluence. If you're looking for a 60 watt Jasper femtosecond laser, a fiber, all fiber high power femtosecond laser, these guys are gonna eat the market alive. I would like to say that this is one of the companies that made the most excited in the last years. Fluence, thank you very much for being part of this Cienkowie Parcio. But not only these people make me happy, the one that makes me the happiest is Dr. Francesca Moglia, who is gonna tell us what's gonna happen in the next 2 hours of your life. Francesca.
Thank you very much, Jose, for the introduction. So here you see, this is our agenda today. So we have a mixture of end users, system integrators, and also experts from the R&D side. But we prefer to see our agenda in this way, where not only the speakers are there, the official ones, but also all of you that are there. And so we heard already a bit about the sponsors that are also here, mostly coming from the manufacturing side, so from the supply chain. But we have also many end users. So here on the side, on the top left, you can see we have different end users from different applications that they are really looking forward to listen to what solutions we can give in laser glass processing. We have for them a lot of really system integrators and experts in processing systems. You see here, if I read all through, it will take really long. So it's really nice that you are all here, but we have really many experts in this today, and also some of them are speakers. But if you're not a speaker, please raise your hand if you have some questions that we can talk about. And then, of course, it's a laser glass event, so we cannot miss the glass manufacturers. So it's really nice to have here today 4 of them. So some Epic members, some not Epic members. So it's nice to welcome new and old friends. It's really nice. And then, of course, the supply chain wants to listen to all of you. And so there is laser system engineering expert, optics, optomechanical beam shaping system providers, machines for glass already, packaging experts, and also the laser glass processing of the future, as I like to call it. So research and development in this field, also many participants today from this. So now we don't want to steal more than this time from your time for the meeting. So I guess we can go back to Jose.
Just to remind everyone that if you missed your logo in that slide, all you have to do next time is register to the meeting, because that slide only resembles the companies who registered for today's meeting. The meeting today is also about connecting companies. So for those of you in the Zoom room, remember that you can arrange for a one-to-one meeting after the event finishes. All you have to do is send a private message to Suzette Germer during the meeting. In the private chat, you will receive instructions on how to join these one-to-one meetings after the previous meeting. But now I also want to say hello to the people in YouTube. Hello YouTubers, how are you doing? Great to see you today, glass processing. Remember, to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asa.com. I will be more than happy to make that introduction. If you have any questions during the meeting, please post them in the chat, and let's start today. And let's start today with what the meeting is all about. The meeting is all about understanding what are really the user needs and trying to find the connections with them. So we had an agenda prepared, and 2 hours before the meeting, we received an email. We received an email from Marc Galiazzo. He said, I'm interested in discussing these slides. We have a look at the slides, and we are in love with Mr. Galiazzo, R&D manager of Applied Materials, because he understood what this meeting is all about. He has a Santa Claus Christmas list. Marco, grazie mille. Thank you very much for being with us this afternoon. What are you asking Santa Claus this Christmas? The floor and the attention of everyone is yours.
Thank you, Jose. So kind introduction. Let me share my screen. And not here, but here. What's all about? So who am I? I'm R&D manager at Applied Materials, Italia. So we're based out of Venice, very close to Venice. So also a nice location if you want to come and visit. After COVID, of course, you're always welcome to a very nice part of Italy. And I'm talking here as R&D manager. So let me try to minimize this. So I lead basically the R&D development for this company. It's a fairly old company. So the Bacini was established in 1967 by Gesulfo, and he was a pioneer for automatic screen printing lines for microelectronics and PV. So it was first in Europe, basically to propose the technology, and his basically his vision allowed basically to start a full industry in Europe. And in 2008, actually, this company that had back then quite an impressive growth was acquired by Applied Materials, and Applied Materials is based in Santa Clara, is a NASDAQ big semiconductor company. Maybe many of you know this group. So we became a branch of this big multinational company, and we were incorporated. And just to give you some figures, for example, in PV, we have more than 2,000 systems worldwide. Now, I would say mostly in Asia, because the market shifted in the last 10 years to China, Malaysia, these countries. And we cover for PV still the screen printing. We have an effort in module, so equipment for module making. We have also laser processing among our expertise for silicon in this case, but of course this is not covering the full scope of this workshop, so I will skip that part. But of course, again, I would be interested in talking also about silicon processing. And here we will talk about print electronics. And we have an effort which is mostly related to R&D. And we have a display. So among the branches of print electronics, we are extensively investigating display. So with display, there is an opportunity of related to screen printing display, but also for laser processing on display. So I came here with actually a wish list, so I don't have too many answers for you. I have more questions. And I have two relevant applications, and both of them have customer behind. So of course, we are mostly looking at equipment, so integration of laser into a full system, but customers come to us with requirements which are related to the final device or final product. And this one is the first one. I put here in quite general terms, so you can have just an idea on the basic understanding about this process. And we're looking at substrates which are approximately, let's say, the usual up to A4 size, so maximum 300 millimeter by 200 millimeter. The thickness is ranging from 500 microns to 1 millimeter. And the via diameter for this specific application can be as low as 40 microns and can go up to 100 microns. So the aspect ratio ultimately can go as high as 10. So is the diameter to thickness ratio. With the via distance, that can be from 100 to 300 microns. So this is an example of the pattern, and this normally would go all around the substrate. So basically in the four sides, and this is related to some advanced display technology that big companies are now looking at. So it all is added up to around 3,300 vias. I would say that for this kind of application, being a kind of still exploratory phase, we don't yet achieve tight requirements in terms of cycle time of machine throughput. So it's more of R&D phase, and people now want to understand the highest quality they can achieve and to build this device. Okay. Another application here we have also a specific class we are basically targeting. This is the model. It's a Corning SGW3. So ideally, we are also flexible and open for different kind of glass, but I would say with a similar kind of requirements. Here, the thickness is set at 500 microns, and also the substrate size is basically 16 by 16 centimeter. Here, the requirement on the taper is quite tight because the maximum taper should be between 1 and 2 degrees. And this is a sample. So we are doing currently some sampling for this customer. And we have a specific layout of an array of holes with variable diameter. Pretty much the same requirements as before, plus, in this case, 4 holes to the corners with 700 microns. And here there is also an added requirement in our wish list, which is about the basically tweaking a little bit the surface behavior where we process with the laser. So if we could ideally increase the wettability inside the vias, this could be really a big breakthrough for this application because we need to apply some materials, as you can imagine, inside these vias. And we have an additional requirement. So this is also to be kind of met or understood. So the full substrate should not go higher than 200 degrees C because there are basically structures which have been pre-deposited that can withstand up to this temperature. So I understand this can be fairly tight requirements, but I'm sure among those companies and the names I saw, pretty impressed by the audience. So I think somebody can also knock at my door and try to help us in this journey. So thank you for your attention.
Thanks a lot, Marco. That's really, if you were never there before, this is exactly what we like when there are specific data, specific information, specific requirements, so that our photonics expert here from integration from laser manufacturers can maybe ask you something or already go deeper inside the request. So I see now maybe there is a question from Wilfried. Wilfried, please, you can open your microphone and ask from Zeus MicroOptics.
Hello, can you hear me?
Yes, a bit quiet, but if you can.
Yes, I have some problem with my headset all day already.
Okay,
And,
but we can hear you. If we stay quiet, I shut up now.
Okay.
It's good. It's good.
The question is fused silica. What can we do with fused silica? I know WOP can do it. I already talked to you at the last EPIC event. But what I've these holes. We need to get drilling in glass without any post-processing. So because sometimes we have other layers on it, and we can't afford any post-processing in general. So the question is if you can do directly drilling, and what about if there's any debris then that has to be removed, or if the surface can be protected with some polymer and that can be removed. This is a question.
Okay, very good. So now we have multiple questions. So all the system integrators and laser manufacturers has to answer multiple questions. So don't be shy. Who is for questions? So yeah, Antanas, of course. You were really asked explicitly, so you have to answer some of these questions, please.
I have a question to Marco. So in the first request, what are tolerances for diameter? First and second, both.
For both, these I need to find the tolerance, but are fairly tight, especially for the second one. I think that having the tapering requirement that what is it, 1 to 2 degrees, this goes with the fairly tight tolerance. But,
and along with that, roughness of the side wall, is it critical or not?
For the second request, for sure, because they are the deposit, the material we're going to deposit, and as I mentioned, the wetting behavior is fairly key. So to have kind of as smooth as possible of a surface could be.
You know, it is related to wettability as well.
Yes. Yes.
Okay. Okay. Thank you. I got the answer.
So anybody else who wants to listen and answer to this, all these questions that were made from Zeus Micro-Optics and from Marco now from don't be shy. We will. Yes.
Marco, I have a suggestion for you. Maybe you should contact ASMPT in the Netherlands. They have laser dicing machines, but I think this application might be also working for you. To roughen, to make the holes more smooth, they also have a etching process.
And etching, yeah. Yeah, we were looking also at two-step processing. So kind of not only direct laser, but combined laser and etching.
Yeah.
Very
Thank
good.
you for the recommendation.
Recommendations are also good. And
you're welcome.
Thank you very much. Then do we have other suggestions, ideas? I see at the beginning you're always shy. Because I tell you, the next speaker is another end user. And if we sum up all these questions at some point, we will come to you and we'll ask them again. So I see you're shy. In worst case scenario,
I'm not shy at all. I'm crazy. I cannot wait. I cannot wait. So you were talking about the hydrophobicity aspect. So when you're talking about the glass structure, your idea is to actually have it the surface hydrophobic and then increase the wettability in the holes. Is that correct?
Yeah, to have a kind of selective behavior. Yeah.
I'm gonna shoot in the air now. Is there anybody from Bionimetric in the room?
Yes, we're here.
I get no commission here. Can you help Marco?
Okay, help him with respect of the wettability.
Yes.
So from as far as I understand, I think Marco is trying to solve the problem of the glass becoming, let's say, more hydrophobic after processing. Is this correct?
Correct. Yeah.
So
to promote the wetting inside the material wetting inside the hole. Yeah.
And you just want it to be the same as it was before?
You mean by?
I mean, you'd like it to be hydrophobic or not?
No, I would say hydrophilic inside the hole.
Hydrophilic.
No, what he wants is you have the glass, right? And then somebody with the laser industry gonna make holes on them, right? Very nice holes. And then Marco says, I want the surface of the glass to be hydrophobic and the water to go in the holes. The holes hydrophilic, but the purpose here is to make the surface hydrophobic. I know you can help him.
Yeah, we have a solution to make the surface hydrophilic, though not hydrophobic.
Hydrophilic.
Yes, and we can discuss in detail for that if you would like.
Okay. Yeah.
And maybe you spend also a word about what biomimetic is, right? Now that we have the microphone, take your chance.
Yeah, of course. I would like to thank you for this excellent organizing event. Biomimetic is actually a really fresh spin-off company. It was founded now within September. It was we started. We are doing glass surface functionalization just with laser pulses. So we are actually in product development now, and our main objectives are anti-glare glass surfaces, and also some super hydrophilic, let's say, anti-fogging glass treatments.
Very nice, very nice. So good luck with this. I really think you have really a lot of opportunities out there. EPIC is also committed to this functionalization with lasers, with our LAMPAS initiatives. So we are really tell you really good luck with this. And yeah, maybe it starts with this. When you can talk with Marco, who knows?
Thank you very much.
Yeah, you're welcome. So I guess that we maybe go on with the agenda. So in the meanwhile, you get a bit more less shy. And so now it's time for our AR/VR application. So thanks a lot to Arseny for being here. And I guess the floor is yours when you want to share your slides.
Thank you for the introduction, Francesca. Let me just share the screen. And I will go into full screen mode. So I hope you can see it now. So let me make a start and introduce myself and WaveOptics. So we are a company which is designing and manufacturing two key components for augmented reality, namely diffractive waveguides and light engines. And I'm senior manager responsible for waveguide development. So that's a bit of the history of the company. So we started trading in 2014. We're still a startup, but a large startup with 110 people. Up to date, we raised in excess of 60 million. And as I mentioned, we focused on manufacturing those two key components for AR headsets, which are AR lenses, augmented reality lenses, and small projectors, which we call light engines. So inside the company, we've got experts in different fields. We've got people specializing in modeling. We've got some in-house developed modeling tools. We've got manufacturing specialists, metrology specialists, and people focusing on the optical testing. And as you can see from this world map, our main headquarters are based in Oxford in the UK, but we've got business representatives in around the whole world. So this slide shows our range of augmented reality lenses, AR displays. I'm probably not going to go much into details here, except of mentioning one thing, that we are producing 3 different products, and as you can notice here, they can be 1 plate, 2 plate, and 3 plates. This means that, for instance, for our 3-plate design, we've got 3 waveguides which are individually cut, and they are stacked together to form the final product. So moving on to the next slide, this is a similar slide just showing the range of light engines, which are small projectors, which we're also manufacturing. This product is not that much relevant for this meeting, so I'm just going to skip this slide and move on. And on this slide, you can see our full manufacturing cycle, and I will spend a couple of minutes just discussing what is on this slide. So the way we produce our diffractive waveguides is by using nano-imprint lithography. So it starts by imprinting diffractive nanostructures onto large 300 millimeter or 200 millimeter high refractive index wafers. After the imprinting is done, we apply some optical coating, and now comes the relevant part, which is laser cutting. So we are using lasers to cut out individual lenses or waveguides out of a large glass wafers. After this, if it's a two-plate or three-plate design, we assemble them together. So we attach one piece to another. After this, we apply edge blackening. So this is a blackening material which is applied at the edge around the perimeter to absorb the light which is escaping the waveguide. And finally, of course, we test them. This slide shows in a bit more details our assembly process. So we, as mentioned, we start with individual waveguides which are cut out of large wafers by laser cutting. And then we stack them together using an adhesive tape and applying some pressure. So we press them against each other and the tape works as adhesive material. We repeat this process to add cover glass, and finally we jet dispense blackening material at the edge. So this slide is almost the last one. This is just in the epic style. I want to talk a bit of what we can offer to our partners and customers. You will notice that the first item is that we do quite a lot of co-development together with our manufacturing partners, and we are willing to provide our own expertise, for instance, in the field of advanced R&D metrology, which we developed over the years. So we are open for this kind of co-development collaborations, because what we find is that many solutions which we're introducing are very challenging, and it's not like we're getting them off the shelf, but sometimes we are working closely with external partners to create something new. And of course, for our customers, we offer our products, which, as mentioned, are waveguide and light engines. And the last slide from my presentation is my wish list, which I actually just changed a bit after the previous talk, editing one item. What you can notice here is that the first item on this wish list is laser cutting with very vertical sidewalls. So we need them to be really flat and vertical with variations in the micron range or even sub-micron range. This is very challenging, but I'm wondering if someone can help with this. It doesn't necessarily need to be laser cutting, but any process which can ensure very vertical and smooth walls will be much appreciated. And the item which I added after the previous talk is we actually also want to have this surface hydrophilic. The other item on my list is that we're looking for assembly solutions to attach two plates together with micron scale precision. And those are just a couple of suggestions how this can be achieved. The first one, I'm not sure if it's very relevant for this community, but we're looking for optical glues with refractive index below 1.1. But also some glass bonding solutions, such as offered by SCHOTT, and I borrowed this image from the SCHOTT website just to show that I understand that this kind of packaging already exists, and we are interested to explore if we can apply this solution to our waveguides as well. So yeah, that's the end of my talk. Back to you, Francesca.
Thank you very much. It's really, really great to have WaveOptics in Epic. And every time that you give a presentation, you always give us your wish list. And now here is twofold. I leave the slide on because I want to repeat them. We are looking for glass cutting with vertical sidewalls, with micron, even sub-micron range tolerances. And they have to be the surface hydrophilic, as we just talked in the previous presentation. And we are also looking for partners on the precise assembly. So let's see, let's find you partners, collaborations, and potential customers. We have a question here coming from Forget. Marc, what's on your mind?
Yes, hi, thanks. My question is, what kind of optical surface quality do you expect when the surface is made hydrophilic?
Thank you for this question, Mark. Actually, optical properties are probably in this case, I mean, there are two solutions for us, because if the surface, we either need it to be, I need to clarify it. We either need the surface to be absolutely flat and vertical, then we don't need to have it hydrophilic. But if we want it to be hydrophilic, then optical quality of this first surface doesn't matter.
Okay. And what type of glass are you using? Is it fused silica?
We're using high refractive index glass from suppliers like SCHOTT and Corning. I don't know actually details of what is this glass, but I assume it is highly doped some specific flint glass.
Okay.
Most likely.
I have another question regarding the cutting edges. You were talking about the vertical cutting edges, right? That you expect when you cut out the glasses from the mother piece, whatever that is. Have you thought about laser filamentation here, or what type of cutting are you using so far?
And right now we're using some standard laser cutting. Unfortunately, I don't have those details probably which you're asking for, but it's not a specific solution. It's one of the standard solution. And if there is some other technique which can guarantee more vertical sidewalls, I would be really interested to learn more details.
Okay.
Fantastic. And now we go to coherent. Joris, what's on your mind?
Sorry, I was muted. Yeah, so I actually want to add to what Marc Hüske just said, and that is that filamentation cutting, where you first basically micro perforate the glass and then subsequently separate it, is a absolutely vertical sidewall cutting technique, and it's actually well known in the industry. The question that I have is, how thick is your 3-plate waveguide product? Because that could be the most important parameter there.
Thank you for this information, Joris, and for the question. So our 3-plate has, each plate is 0.7 millimeter now.
So the 3-plate total is 0.7 or together 2.1?
No, it's each plate 0.7 millimeter.
Oh, so 2.1, okay.
Yeah. But we are, of course, looking into thinner glass, but right now we're obviously cutting them one by one.
Okay. Oh, so you first cut them, then laminate them effectively one way or the other, and then post-process them.
Yes, that's correct. But we're also open to consider first bonding them together and then cutting. And actually, this would be arguably even more interesting because from my understanding, we can increase throughput as well significantly by doing it this way.
Yeah, that should be fine. Yeah, and I also saw that I cannot read from who it is, that the technology that was pioneered by Professor Duncan Hand and Harriet Watt, that is also something that we have been working on in Coherent as a tool. So that could be something that could actually help you with the bonding of those plates, and that would then be a laser welding solution of the plates. And you actually optically contact them. So the request that you had for the sub 1.1 refractive index glue then seemingly goes away.
Okay, I'm going to take this chance. So if Professor Duncan Hand is watching, Duncan, it's really good to hear from you. Great that everybody has such a huge opinion of the amazing work you have done in Scotland, and it's also a good friend of mine. So great, Duncan, that you have been mentioned at this meeting. We're going to go to Israel because Natan has something on his mind. Nate?
Hi, thank you for this chance to speak with us. So what we hear about this filamentation cutting chimes in with the product of ours, which is Deeply. Launched it recently. I'll try to share it. 1 second. Here. So if you need to cut very thick glass, one of the standard ways to do that is with bezel beams using Arseny. But as we all know, the intensity profile for these things is not so ideal. So sorry, if you can see this movie, by the way, is it playing? It seems my internet is a bit slow. Here. Sorry, Jose, do you hear me?
Yes, hello? We can hear you and see you. It's all Jose? Good.
Oh, great. Sorry, because I'm not getting anything back. So one of the ways to get this sort of nice filamentation cutting in thick glasses while keeping the focus very thin and narrow, can be 3 microns, is to do it with ultra short pulses at around the 1 micron regime, and use special optics for cutting, such as our deep cleave, that can give you easily, this is for 1 millimeter in air, but in glass it would be 1.5, and we can easily design for 2 or whatever is needed. And using this in some sort of finishing process, it's quite easy to achieve a large depth of focus cutting. So basically, we are looking for partners to test it with, so we'd love to help anyone that would like to develop the process, for example, for Waveguide. Thank you, Jose, for this opportunity to speak.
Thank you very much, Nathan. Thank you for joining the meeting. Whoever, anybody's looking for a partner on making an instrument with diffracted optical elements, you need to go to Holo, or because these guys know what they are doing. It's great to have Nathan with us. It's great to have also WaveOptics. Arseny, many EPIC members are contacting you, interacting with you, benefiting from your challenges. This is what we want, because WaveOptics is one of the success stories of the European ecosystem. Bringing nano-imprinted optics to the consumer market was a huge challenge, and you are there, you are doing it, and you make us proud. So Arseny, once again, thank you very much for what you're doing for the photonics in Europe.
Thank you, Jose.
I think it's time to continue, Arseny, because we are going to have a lot of companies, one of them, for example, Primoceler, mentioned in your slides, that can help you with your support. But first I go to Lithuania. I go to workshop of Photonics. It's one of the places where I enjoy the most when I visit companies. Thank you very much for being with us at SCHOTT. The chief research scientist, Antanas, is here to help us build a laser for glass. The floor is yours.
Thank you, Jose. And very briefly about who we are. Self-introduction. We are private-owned company located in Vilnius, Lithuania. We work together with R&D institutions in universities and industries, and we developed our own technologies, and we also take licenses from other technologies. So that's why we have possibility to use 9 dedicated femtosecond laser setups for fabrication of glasses and so on. And a couple of years ago, we started using wet etching along with laser fabrication. And recently, we were certified on ISO 9001. So why we talk of glass? Everybody knows that glass is a good material for MEMS, microfluidics, and so on, because of thermal stability, chemical resistance, possibility to reuse, and so on, and all the features I listed here. Of course, it will never be as cheap as plastic, and it will never compete in MEMS or microfluidics with roll-to-roll plastic fabrication. So we don't tend to mess in it, but if you need durability, if you need harsh conditions, so glass is yours. And then very briefly, what we can do, and I will try to comment this video. This is forecasting Jose's question, what we can do for the community. So all this is yours if you need it. So as you can see, we can handle the tasks from first speaker. We do a little bit more holes per wafer, and even a little bit smaller. So how we do this? As I mentioned, it is dicing, scribing, ablation, laser and etching. So, and I promote in any opportunity on EPIC meetings and other meetings as well, that think out of box. You can use glass instead of very many materials. And here is one example of alumina ceramics replaced by glass. You can see the quality of the hole in the ceramics, which is used as part of the Pozo probe. You simply check what you need instead of that ceramics, depending on what is important for you. You choose the glass and you get it. And you get much better quality than you can do by ablation of ceramics. But this is not only holes we can do in glass. Here are some examples of what we provide to the customers who come to us with their problems. You can see skewed channels in the glass cube. We can make sandwich of 5 glasses for microfluidics with different channels in each layer, with welding the glasses, all 5 layers welding together. And here is an example of microchannel area for positioning of fibers. You have to make it conical to make easier 120 micron fiber to come in. This is top view, and this is bottom view, and you have the area for irradiation or something. I don't know what it was it used for, but we make like this. Not very easy, but we do. So if someone decided to go for glass, just know, then you have a partner ready to develop a process technology for you. You can get a lot of what laser and wet etching or just femtosecond laser can do with glass. And before you go to volume production, we can provide you this contract manufacturing service. And it is up to 1,000 pieces of 8-inch wafers per month. And you can expect all these nice things you saw on the video on your product. And it is quite quick turnaround time. And if you need, we can provide you with light engine to make your process in your facilities. We can provide you with laser machines that enable the processes we develop. So that's it. I almost fit in 6 minutes.
Very good, Antanas. Thanks a lot for your presentation. So you have now a very good excuse. You show us a video so that you didn't talk too much. So now we have to make you talk more. Okay. Now I just, so we heard already from some end users so far some requests. So you commented already a bit about it, but we left basically Wilfried a bit without an answer. So can you comment again about if it's possible for you to drill without debris, if you can undisclose your tricks? Otherwise, don't and speak with Wilfried.
It is no very special tricks. Usually you do this either with wet etching or with ablation. If ablation, this means debris. You cannot avoid it. So some particles will sit down on your surface. But wet etching, it depends what coating you don't like to damage. So Wilfried, it would be good to know. So what is on your fused silica? So if it is not very sensitive, let's say to alkali etching, then we can do it very clean.
Mm-hmm. Well, can I talk or?
Of course.
Sure, you can talk.
Yeah. Yes, well, it's typically AR coating. So we don't always know the composition of the AR coatings. So I don't know if they resist these alkali etching steps. It's always difficult to say. The other problem is if we use the etching, so and then the parts will fall apart. So this doesn't work for us either. So if we want to use it for example, waste chip dicing or something, then so we need a substrate. So if we would use etching, then the elements still have to remain on a substrate. So I don't know if this would work with your process.
We can discuss it offline. I think a lot is possible. AR coatings are quite resistant to alkali etching.
Yeah. Okay.
So we are not used to have Wilfried as end user. So you see how demanding he is. Thanks a lot, Wilfried, also for this. So now I see we don't have further questions to Antanas, but we have so many people, new and old people here sitting. So I would like now maybe to give a couple of seconds, no, not seconds, but a couple of words to be said by some of our new guests. So for example, Thorsten from ISFH. Do you hear us? Remove the glasses. Now he's ready to. Thank you, Thorsten, for being here. Can you a bit introduce yourself and also your activities?
Yes, hello to everybody. My name is Thorsten Dulbiber from ISFH in Hamelin. We are a solar energy research institute. We are developing silicon solar cells for the PV industry. We collaborate with several companies in Germany and all over the world. And we are in an early stage to also look into how we can apply structured glass in this activity. So hello to everybody. Nice meeting you.
Thanks a lot, Arseny. So he already mentioned something. So who has ear to hear can pay attention and maybe talk to him later on. Thank you, Thorsten. So now, if there are no other questions, we can go on with the agenda, because now we talk about SCHOTT Primoceler already. So now it's maybe time to give the floor to Ville so that he can really speak about his expertise and what he can offer to this audience and what he can request. So the floor is yours, and he's almost there in presentation mode in a second, I assume. There you go. Awesome. Thank you.
Oh, can you hear me?
Yep, very good.
Good. So thanks a lot for the invitation. And one thing I have missed during the strange times that we are seeing is the energy that EPIC and the people here are giving. So really great to be here again. And today I will be discussing about ultra reliable miniaturized glass packages. And coming from a company called SCHOTT Primoceler. But so who we are? Sorry, I'll just put the timer on so I will not talk too long. So here we go. So who we are? So we are, for example, the ones that help the blind people to get their eyesight back, or the vision back. Of course, we do not do this all alone, but we have developed a technique to produce hermetic packages, for example, for medical implants, for microfluidics, and actually now more and more to microelectronics and micro-optics. So the company itself, we are based in Tampere, Finland. You probably can hear it from my accent as well. And we actually joined the SCHOTT family around about 2 years ago. So now we have a lot of more muscles behind us, what we do here. And we have developed a additive-free room temperature hermetic glass bonding method that it was nice to see that at least two of you guys already have mentioned similar technology, so might use our help. So I'm sure that there will be a lot of further discussions to go through here. And why I was saying that we help people to get back their eyesight is that one of our customers, for example, what I show here, Nanoretina, they are building up a retinal implant that's implanted in the human eye. And this basically restores part of the eyesight for people that have sometimes had the ability to see, but now for some reasons have lost their eyesight. And it's really more than motivating to be part of such activities. But what we are doing is basically we are forming hermetic packages. So we are using laser light to shine through glass sheets and join the glass sheets together. And like also in the previous presentation was mentioned, this way you don't need any adhesives or additive materials. And here are some example pictures of, let's say, live devices we did 7-ish years ago together with the European Space Agency. So first we focused mostly on high reliability, high cost level devices like medical implants and aerospace. But thanks to SCHOTT, we are now taking further steps. In the past few years, we have developed the technique for higher manufacturing numbers, so volume manufacturing. And at the moment, we are focusing on wafer level processing. And here, maybe you can see my cursor. So what I'm showing here, great. So we are building up stacks of glass or stacks of glass and silicon, and bonding the wafers in wafer form. And why we have done this decision is that we can then use standard processes from the semicon world, whether it's thin film coating, someone mentioned here AR coating, or metallizations. So we can apply the standard processes from many steps and introduce our bonding method here. So we stack up wafers. We can put devices, electronic devices, inside the glass. Sometimes, of course, the devices do not need to be active. There were many companies doing micro-optics or diffractive optics here. So of course we can have passive elements also in the stack. And after we have done the stacking itself, then it's time to dice the devices. And here again, we can use the standard techniques, whether it's laser-based dicing or blade dicing, to dice the chips into individual devices. And to get some numbers, so we commonly have on a wafer, we commonly use 8-inch wafers. So we have from some tens to some thousands of devices per wafer. So this really is already a quite well scalable process that can be used also for higher volumes. And just a side note here that for high volumes, our colleagues have also developed a technique to do glass structuring in wafer form. So if you have a need for higher volume, precise glass structuring, you're more than welcome to contact me or our colleagues here. So if you need spacer wafers or cavity glasses or camera lenses, so please feel free to contact us.
Thank you so much. When I see the progress, the success, because we know each other already for many years before Primoceler was acquired by SCHOTT, when I see how you are helping the industry with key innovations and what you are doing with the company in the implants on the eye, this is quite amazing. And you are one of the reasons I'm happy every morning when I have to do this kind of job. Thank you once again for what you're doing. We have questions for you. And the first one is from the Photonics company of Europe. I put Osram like that. Roland, what's on your mind?
Yeah, hello together. So I'm interested in regarding both surfaces. If we bring both glass surfaces together, what is requirements for roughness, smoothness of the surface of both glasses that you can do the joining with your Primoceler process? Do we additional polishing or can we use glasses which came from the suppliers directly? What is the requirements for the surfaces?
Yeah, so the beauty with the glass wafers we have seen, we have I think 4 manufacturers were mentioned already today. So we can use standard polished wafers. So there's no need for any higher polishing.
Okay, sounds good. Thank you.
So in the beginning of the meeting, well, thank you, Roland. And if you have any other question, people really want to work with Osram. It is great to have you in EPIC. Thank you very much for supporting. Ville, in the beginning of the meeting, we had a really, really nice presentation from my very good friend, Eugenie, who really was saying, I think I foresee at least a collaboration with you on the field of glass bonding solution. Arseny, are you still here?
Yes, I am. Hassan.
What do you want to do with Ville?
So yeah, I borrowed this image from the SCHOTT website, which is showing this nice glass packaging. But I just learned from the presentation that this can be even done on the wafer level. So you can see actually on this slide, quite conveniently, you can see one of our wafers at the middle at the top. This is how they look like with individual devices imprinted on them. So what would be nice if we can, of course, if we would be able to bond those wafers together and then cut them. And I mean, we are using already wafers from SCHOTT, so it seems like it's a nice expansion of activities with SCHOTT in this field. So I would be really interested to discuss and look into this opportunity to bond those wafers and cut them.
Yeah, I'm pretty sure we can help you, and this is one of the reasons we are part of EPIC. So actually, it was like a half an hour ago, so I got a calendar invite to have private discussions with with you. So that's why we are here.
We have even, of course, questions in the YouTube universe for you. The first one is from a company in Denmark, NKT Photonics. They make fantastic supercontinuum laser and fiber lasers, and they saw your process. So Hussein Iman saw your process, and he's wondering, he can ask you the epic question: what is your wish list on lasers? What could be the laser that you are using today? You could specify a bit, and if you could have any laser in the world, what would be the dream laser that you would like to have?
To be honest, we are quite fortunate to be located in Tampere. so we have a lot of all the optics research here is rather extensive, and for the moment, I'm not sure if I'm speaking on behalf of all our R&D engineers, but the light sources at the moment it's on sufficient level, and so this is the beauty. So the technology in the light sources is really in the already really industrial, and lasers can be used in industrial processes without having to tune them every day or even every week or even every month.
Further questions. The first one is from an entrepreneur in a stealth mode. He doesn't want to say the name of his company, but he's asking, this is a big business opportunity. He's asking, can you do bonding of glass and plastics?
So plastics, I would say that the short answer would be no, and that's for the so if we are to melt the glass, that's already the temperature is such that the plastics in general would evaporate already. Of course, it depends. There's many kinds of plastics, but the general answer that sorry, this is one thing that we probably cannot help with.
All right. So one thing, Ville, we are living now the era of micro-optics. This is the revolution of micro-optics. I see companies that are really booming in this field. And so many of them you have heard already from EVG and from WaveOptics and from micro-optics and from NILT. And they are really developing technologies never seen before. In Europe, CSCM is making a big difference on actually bringing all these companies together. Perhaps Ronnie has a potential collaboration with you. Let's go to CSCM. Ronnie, what's on your mind?
Hello, do you hear me?
Yes, loud and clear.
Yeah, I'm also Jose, actually. My last name is also Jose. So we have something in common. But I had a question. It's not a requirement. we have also a complementary technology also with laser actually bonding. But it's with metal, thin film metals actually. So my question to you was actually, is there a gap between the bonded parts actually when you bond it together, or is it really in optical contact?
So here it's in optical contact, and this is one of the key benefits that we are able to offer. So for example, we mentioned the micro-optics here. So if we are building a stack from 3, 4, 5 layers, then the gap tolerance can start to be a bit of an issue. But with our technology, we can reduce the tolerance to basically only 0, or to the tolerance that the glass wafers themselves have been processed, which is with today's techniques rather good already.
Okay, one more question, maybe about the wafer level bonding actually. So is it actually, do you have a very good yield on the whole wafer, or is it like it's still in development actually?
Of course, this is product dependent, but of the products that we have done the development and the manufacturing freeze, then we already receive really high yields.
Okay, thank you very much.
Any further questions or suggestions? I have a question from Joris from Coherent. What's on your mind?
Well, I just made one note, thank you. That is, there was just a question about polymer on glass. I don't know what the bonding needed to be, but I remember that polymer on top of glass for optically transparent is, of course, something that Anterion was always doing. And I just wanted to put that as a suggestion.
Yes, and all the way I would like to say hello to my friends in Eindhoven and congratulations on the great success that Anterion is doing in the field of micro-optics. Thank you very much, Joris, for that. I have a private message from Biomimetic asking for more information about the person who was challenging on glass plastic bonding. I cannot reveal the name. However, what I can do is that give you the floor, and what would you like to know more about this glass plastic bonding?
Okay.
Evangelos, yes.
Yes, thank you. We would like to know some technical information regarding the adhesion forces that they would like to succeed.
How can you help them? What can you do in the field of plastic and glass bonding?
We have something in mind, but I cannot disclose it for now.
Everybody sharing their secrets in this beautiful meeting. Let's continue with the agenda. I think today we have a lot of room for cooperation. I like when we close the gap with all the different companies, and the company is going to bring all of us together. Today is in Hannover, and it's Laser Zentrum Hannover. We had the luck of having with us the head of glass group, Arndt Hohnholz. Arndt, thank you very much for being with us this beautiful afternoon here in the Netherlands. I'm sure the weather is also great in Hannover. The floor is yours.
Yes, thank you, Jose. It's quite cloudy out here, but yeah, we can enjoy the weather. And thank you very much for your kind introduction. So for me, it's the first time for an EPIC meeting, and so far I really enjoy it, and there's a very nice discussion. So thank you also for the opportunity to show our topics at Laser Center. So Laser Center is a non-profit research center, and we are about 180 researchers dealing with a lot of different types of research topics. So on the one hand side, we are working also with the coating of optical elements with functional coatings such as filters or anti-reflecting coatings, thin film coating systems. And yeah, if you're interested, please contact me. On the other hand, we are also working on fiber lasers, the production of fiber lasers for special applications for space, for example. And yeah, I'm more on the focus on the glass processing with the laser. So let's have a look to our working group. We're focusing on not only the quite conventional topics such as marking, cutting, and drilling, where I will give you an introduction, but we're also doing the welding with, for example, CO2 laser or also a CO laser for joining different glass pieces by using an auxiliary material. And here we are providing a fiber into the process zone and heat it up, and then we are melting it together. So this fiber can be also used for additive manufacturing. So Jose, you said something about metals. Yeah, there are metals and polymers, but we're also trying to do it with glass materials. And yeah, third topic is the coating, coloring, functionalization. So we can also use the ultra short pulse lasers, for example, to do the nanostructuring of the surface for some functionalities. So I will talk a little bit more into detail of the cutting topic. We're aiming at Laser Center Hannover. And yeah, maybe you know this already. Glass is used in a very wide of applications, displays, electronics, architecture, of course, for thicker glass boards, and even other applications where you have high temperatures, corrosive environments, and so on. So when you talk about glass cutting, you concentrate of the chipping, the stress, and the surface roughness. And yeah, here we did a collaboration with Labs together, and yeah, they're producing a reflective asphericon. So an asphericon transforms your incident laser beam into not only a very fine focus, but you can use it also for an elongated focus. So we can elongate the intensity profile to manufacture or to process even flat glasses for very constant intensity profile. And of course, the conical shape on the top will generate these transformation, and you have the interference effects, and this leads to this elongated beam. So in our case, we want to use it for the ablation, and we developed a setup for this. So we're using two collimation systems. The first one is before the asphericon, and the incident laser is guided onto this asphericon that has a active area of 50 micron, and then of course a second collimation brings the laser spot onto the surface. And here we can combine this with a galvanometric scanning system. And this enables the area processing with this bezel beam. So of course, this needs quite a long time for adjustments, because you not have only the angle to set up, but also the mirrors before and behind. So you have to really focus, or you have to really aim for that spot on the asphericon. So giving you a glimpse of our results, you can see our cutting techniques by one pass cutting with a femtosecond laser source by amplitude. And here we are using 550 micrometer thick glass, and we could yes, do it on the whole area. And fine features are possible, of course, by cutting off these glasses. And yeah, as you can see in the bottom right picture, we have a transformation area. We're just in the beginning of our research, but here you can see that a boundary effects of about 5 micrometer is visible. This, of course, has to be enhanced. And yes, here we are open for some collaboration in different fields, of course, and I'm open for questions. Maybe one more detail. We can adjust the focal length by adjusting the collimators. So here we adjusted it for the thin glass, but we also wanted to adjust it for thicker glass as well. So thank you very much for your kind attention. Thank you, Labs, for the collaboration. And maybe a very short glimpse to our workshop. So we have a yearly workshop dealing this year for additive manufacturing, serial production, and architecture. If you're interested for German language and German spoken talks, then you're invited to follow us on our website and to join in our webinar as well. So now I'm open for your questions. Thank you.
Thank you very much, Arndt. Thanks a lot for your bit of a glimpse into Laser Zentrum Hannover. And now, I mean, we are coming to the Shakespearean question. So refractive or not refractive, reflective or not reflective. So there is Natan from Holo that has, of course, a bit of a more detailed question. So you can ask it maybe directly to Arndt and to the bezel beam people.
So I've noticed you're using a reflective solution. I'm assuming this is an ultra short pulses, so I understand the need for temporal, let's call it keeping the pulse as short as possible. But is it reasonable to work in such an off-axis mode? I mean, if you use a thin diffractive axion like the ones we or some of our competitors make, it has a fused silica plate of 1 millimeter, not a lot of spectral dispersion. Is there a special advantage to using a reflective vessel beam?
Yeah, so the transmissive axion, of course, has this shape on the top of the glass, of course, and of course to manufacture the tip of these axion.
Yeah. The diffractive one, yes. Diffractive axion transmissive, not refractive. It has no tip.
What kind of?
So yes? We and also some of our competitors, we make diffractive axions.
Diffractive. Okay. Yeah, sorry. Yeah. Okay.
We have no apex. Same as the refractive version, but is there some other advantage? I mean, we can also coat with AR. I just wanted to know if there is some advantage to the reflective aspect.
Yeah, so when you talk about the reflective axion, then you, I don't know exactly, so Kylabs can also answer these questions maybe in more detail, but of course, when I think of some damaging of these optics, then of course I can imagine that there might be some advantages for a reflective axion. Maybe if you think of quite high processing times, you can integrate some cooling or something like that. But I'm not sure 100%. So we tested this with a reflective axion. But yes, this is our first experience with this. So I'm also quite open for some diffractive optics, and we are also thinking of going in this direction. And yeah, thank you very much for your question and suggestion as well.
Thank you. You're welcome to try also one of our competitors, but also just know that axions are, of course, one of the solutions, maybe not the optimal one for this.
Sometimes, yes, yeah.
So maybe we can give a word to Kylabs if you want to add something. Okay.
Yes, then, with pleasure. Yeah. Is it working? Can you hear me?
Yeah, very well.
Perfect. Yes. What we have done also with Arndt, an objective of this test was also to show that it was possible to go through a scanner. And we have known from some other customer that it is not always the case with some transmissive axion. So the goal of this setup was actually to go through the scanner to be able to have high-speed processing. So it was kind of one of the objectives we did it. And then I don't know if it's related to what you just said before, Natan, but with the reflective axion that are shown on the picture, due to the way of manufacturing it, we can control very precisely at the very center of the axion. So it then leads to a very high quality basal beam. So we are very, very close to the theoretical curves, energy curves of the axion. So I would say these are the main differences with transmissive axion.
Thank you. So it is a reflective axion, basically.
Refractive, like a mirror. Reflective.
Yeah, no, refractive, like not diffractive. Like.
Yeah, exactly.
Okay, so it has all the advantages and disadvantages.
Exactly.
Okay, thank you.
Thanks a lot for your comment, further comment after Arndt. And I have to say, let me say that these love stories between Lasercentrum Hannover and Kylabs are always those that make EPIC happy. So thanks a lot for highlighting this. Also for us is really rewarding. And anyway, we have nice collaborations in this community. And then we can move to another question from Poland. So Darius from Fluence, right? So you can ask yourself.
Yes, hi. Thank you very much for the presentation. That was very interesting. And I would like to know what glass thickness did you try to cut, and what glass thickness are you actually able to cut with that approach you're using with Kylabs axion?
Yeah. So so far we were aiming for the very thin glass, and it was up to 100 micron. But of course, so this was in one pass. It depends a little bit on the laser source that you are using. So we tested this with picosecond lasers, but also with the femtosecond lasers. And here we had quite a high pulse energy in the, it was around 600 microjoule. And we found out that with the picosecond lasers, we reached the edge already in this context. So this is in terms, or it's a matter of the pulse energy, of course, and the pulse length, I would say. So for thicker glasses, I think we have to improve it a little bit more with the incident lasers.
And what about polymers? Have you tried any as well? Or
so polymers we haven't tried so far. Sorry.
Okay. And what are your thoughts? What are your expectations? Do you have any when it comes to polymers?
Yeah, so polymers, just another story. So we have to take into account, of course, the heat, of course, and yeah, we have to lower down the the pulse energy. We can rise the repetition rate, for example, to the processing. But I'm not quite sure. I'm not the expert for polymers. I think there might be others in around here that are quite experienced with this. So for polymers, I would suggest yes, just a lower level of energy you need.
Okay, thank you.
Thanks a lot for your question. So now that we are coming a bit to the optics side of the systems, maybe it's time for asphericon also to give their contribution to this meeting. So Janet, please, if you want to explain a bit your interest for this meeting, you're welcome. You're muted. Yeah, now
Okay.
it's coming. Very good.
Okay, thanks. Hello, everybody. I try to share my screen. Is it okay? Can you see it?
Yes, very good.
Very good. Okay, just a short introduction of our company. I think to one of you guys, we are well known. We are a supplier of optical components, such as A-spheres, freeform optics, and as well axicons. Also, we produce spherical lenses. And just want to show the second slide, which hopefully works. Oh, yeah, okay. I just would like to introduce one of our products for beam shaping, beam tuning elements. It's the A-Airy shape. And you can create different beam profiles by using this product, such as a top hat, a donut, or a beam waist profile. And you can easily scale by scaling the focal length from the focusing lens. So to create then the top hat or the donut profile, whatever you like. And it's available for all wavelengths from 300 to 1,600 nanometers. So if you would like to see more, just visit our website, asphericon.com, or email us at sales@asphericon.com. Okay, yeah, thanks.
Thanks a lot, Janet, for your little contribution, but always effective. So if you didn't notice, in case it's good to put this topic right now, in the chat and on YouTube, everywhere, we are asking about, so Jose put the real clear question, what is the biggest challenge in glass processing? And now we have the first hint from Natan. So you have 30 seconds to propose it.
Okay, so at least from what we see from our end users, a lot of people, sorry. Francesca,
we can hear you. Yeah, very well.
So a lot of people try to cut using scanning methods. As usual, in all material processing industries, scanning is the best because it gives you the highest throughput and the most flexibility. The problem is when trying to use filament cutting in some self-dicing processes, like usually they use to cut thick glass, you need high NA. You need to focus it down to 3 microns, 5 microns, something like that. And you can't do that with any reasonable scanner. I mean, we don't have ZIL here, I think, but even the best FTTs don't reach that. So right now, the industry is limited to moving the stage in XY, but I don't know if it can go on like this. I mean, with the high throughput, someone needs to solve this somehow with some very, very fancy focusing optics. So that was one of the challenges, let's say, that we see all the time. We solved it for the XY movement with the deep cleave, but someone needs to solve it also with this in the side of the theta, let's say.
That's a good challenge. So
Thank
if
you.
someone wants to comment already about this, do you agree? You have solutions? You don't want to tell Natan because you don't like him, but now you should like him. Tell him. No, I mean, if it's not the case, anyway, think about it, and then we can keep it this on our wish list. This will put on stones forever for the future, so this won't be forgotten. But now I have, okay, we can maybe now go on, because so we keep on the agenda, and we go to the way to Paulius, FTMC. It's really nice to have you here today, and maybe you can show a bit what are your expertise and what you are trying to make it for the future of laser glass processing, or in the present as well. It was good. It was already in full screen. If you go back to full screen, so in presentation mode is good. Yep, there you go, Paulius. Are you muted or not? Because I don't hear any sound.
Okay.
Yeah, now some sounds is coming.
Okay.
The floor is yours.
Yeah, thank you for introduction. So, so I come from FTMC. It's the Center for Physical Sciences and Technology. So it's a state-funded research center. And I'm a head of laser microfabrication laboratory, where we develop different kinds of laser-based processing technologies. And today I will maybe talk a little bit about what we do on glass processing. So basically today I like to discuss two technologies. So it's vessel beam scribing and laser-based rear side machining. And these technologies I would like to compare with conventional technologies, for example, mechanical scribing, diamond saw cutting, water jet cutting, or polishing. So maybe briefly about these technologies. So as for a vessel beam dicing or scribing, we already heard some talk, and so basically here what you need to do is just you need to perform some elongated modifications inside the glass in your desired cutting path, and then you need to apply some mechanical load and to separate your samples. So this is really fast technique in terms of dicing speed. But also it has some disadvantages as well. For example, it can be applied only to low curvature cutting contours. That means you cannot really cut narrow holes and so on. So other technique I would like to talk about is like rear, as I mentioned, rear side machining. So this is a really flexible technique. So actually you focus your laser beam through the glass sample to the bottom side, and by applying some scanning of your laser beam, you can form some cutting path. And scanning layer by layer, you can remove some material from backside in a particle form mainly. So this is a really efficient process, and it could reach up. We reached up to 120 millimeters per minute ablation rate, and what we tried today is we can cut up to 19 millimeters thickness glass. And it's taperless process. So we heard today that we discussed about low taper angle processing. Also, this technique is taperless. You have no taper, so it's completely vertical. Yeah. So and other how to say advantages is that you can apply such technique for hole drilling. You can apply for through cutting. You can apply for 2.5D milling as well. And if you combine such technique with other laser-based techniques, for example, laser modification and etch and chemical etching, so you can make really interesting things and really interesting components. So basically, what we did is we tried to compare these two technologies with conventional ones. We try to compare in terms of, let's say, surface chipping. So I think this is one of the parameters which is really important for the industry. And for example, other parameters like your component failure rates for resistance to mechanical loads. So we can maybe go to some summary of our research. So, for example, if you're looking for let's say, a fast process to dice straight lines, for example, so maybe in terms of laser-based processes, of course, bezel beam is one of them, has an advantage. Also, you can also from the conventional processing techniques, you can apply mechanical like score and break method, which is really cheap. And then yeah, for example, if you are really interested in surface chipping, yeah, so again, maybe you need to consider using a bezel laser dicing or bezel beam dicing technique for if you now really interested in surface roughness. So of course, if you want really low optical quality, of course you need to polish your surface. But for example, rear side processing gives you a really fair roughness of about 1.4 micron. Of course, mechanical dicing also gives you quite low surface roughness, despite that you have really high, large surface waviness. You also try to measure stresses inside the glass induced by these techniques. And we saw that if you want to go to really low, if you need really low stresses produced by processing processes, so you might need to use like a diamond disc cutting, or you need to use any other techniques and then to just polish this affected region. If you are interested, let's say, in a sample flexural strength, so again, mechanical dicing is quite show the best results. Or you can use our techniques and then polish with affected edges. Yeah, so these techniques, laser-based and conventional techniques, has their advantages and disadvantages, and really depends on your process. What would you like to get out of it? So thanks you for attention, and I would like just to mention that in-depth analysis of all these things I mentioned you can find in our latest research paper. So thank you for attention.
Thanks a lot, Paulius, for your overview from the more research side of the technology. So now we have a question in the chat from Joris. I guess it was maybe there were a couple of data more already in the last slide, but maybe Joris, you can ask again. But I'm not sure if the answer was there because I missed now in the table. So maybe you just ask.
Okay, so yeah. So what about question was about glass volume? So it was 120 cubic millimeters per minute. So this now we have maximum.
120 cubic millimeter per minute. Okay.
Yes.
And this is with what kind of laser power?
It's around 20 watt.
Okay.
Very good. So if there are, so I don't see questions at the moment. We have many people here, but it would be nice for me to go on a bit with our introduction to all the audience that is sitting here. So for me, it would be really nice now to introduce Guillermo for Guardian Industries. It's really nice to have you here, and maybe you can explain a bit what is your background, your interest in this meeting, and so that we maybe can help you.
Hi, good afternoon all. Yes, I'm feeling a bit like a fish out of the water here. I come from Guardian Industries. We are a large glass manufacturer, and I hear all these amazing things you do in nano scales when we are actually more focused in the bigger scale. We're talking about, when you talk faster speeds, about 100 millimeters per second. For us, faster speed is almost 100 meters per second. So there are some difference in the scales here. But for me, it is a very interesting meeting. My name is Guillermo Benito. I'm responsible for what in Guardian we call specialty apps, R&D. And for us, specialty is exactly what you are doing. Is all those small things that may not be huge in terms of volume, and for sure it will not be our core business, but we believe there is a significant value to be extracted on those applications. We are pretty good at making float glass. We have some very good experience on making architectural coatings. And we are interested in seeing how the laser can help us to improve or either find new application for our current portfolio or processes. Some of the examples that I think I mentioned already to Francesca is, for example, post-processing. When we are talking about changing the morphology of individual layers, not so much about the glass, but actually individual layers like semiconductors or either metal materials, where you can change the crystallinity by focusing those lasers into specific areas of the glass. So this is a bit of the background of why we are joining this meeting, that, by the way, is actually quite interesting. And why we are interested to continue this collaboration.
Thank you, Guillermo. What a nice words. I promise I didn't ask him to say so many good things. So, but really thank you. And that's the point. So I was fearing that we maybe don't talk enough about post-processing activities and so on. So if someone of the laser guys and ladies that are here who want to spend a comment on this, otherwise we have still the address and the connection to Guillermo. So if you want to talk about it relaxed afterwards, also here in the one-to-one meeting, or maybe later on also offline, please feel free to ask us. So to ask Jose is the exchange addresses guy.
Francesca, we talk a lot about beam shaping in the beginning, and I saw that this is good news. Perhaps I'm trying to find what is the biggest challenge in glass processing, and many of you are telling me in private, beam shaping, which is of course good news for the companies like FISBA or Optimax that are in the room. But we talk about cutting, drilling. I'm very interested about marking. Is there a market for laser marking in glass? When it comes to marking, I always call my friends from Liège, LASEA. Jose, are you there? Jose from LASEA. I think he's muted. He's trying to unmute himself. No. He's smiling. So is LASEA seeing the laser marking for glass as a potential market?
Yes, for sure. Maybe you know LASEA is as well a laser system integrator specialized on femtosecond lasers mainly, but not only. We offer solutions for cutting, joining, hybrid joining. You spoke about polymer with glass. Well, I think we have ideas to make it feasible, but we are commercializing since long time ago what we call Naginels marking. that is marking inside the glass in volume, something that is quite demand, for example, for the pharmaceutical industry for traceability purposes. So I think we have a quite a broad experience in this, and I'm sure this could be applied in any other market that is asking for some special marking inside the glass without affecting the integrity of the material in a fast way and, well, easy to read, transparent, no dust. So,
Jose, if as a system integrator, when you're building a system for glass marking, there are two main ingredients, which is called the lasers and the optics. Let's talk first about the laser. You could specify what is the ideal ultra-fast laser. I have my friends from Poland and my friends from Switzerland, Pozo listening. What would be your Santa Claus Christmas list on that?
Well, I don't have a single one. It all depends on the application. We work with a couple of mainly ultra-short pulse laser manufacturers. I can see one of them over there, light conversion, but not only. But well, it all depends on the application, and we try mainly from the R&D activity of LASEA, that we are quite active on R&D, to be on advance of those needs and be prepared to what the future will ask us to provide. And there is a clear tendency in providing more and more higher throughputs. And for this, there are different strategies. One of them goes to higher average powers, but not only, I insist, not only, there are other strategies. And this asks always to use them in combination with the more advanced optical solutions, like a few of them that have been already discussed during this afternoon. So what is my wish list?
Jose, just one now about the beam shaping. What is the typical beam shape? You could specify a bit the beam that would be the one that you would need to use for glass marking.
For glass marking, we use our more or less conventional LS scan module, just galvanometer scanner by the moment, but we have many other ideas on the way that I cannot disclose publicly now.
I talk about marking, and of course, my friend Wilfred from SUS Micro-Optics, all the way from Neuchâtel, has a comment. Wilfred, what's on your mind?
I just wondered if CO2 lasers, we haven't talked about CO2 lasers yet here. So what is their impact in this whole laser processing market? Or is that obsolete now?
We still use them. We have customers that ask us already for that type of more conventional and known solution. But
yeah, okay.
I also know that Zentrum Hannover also uses them as well for other applications in the glass. Is that right, Arndt?
Yeah, you mean the CO2 laser?
Yes.
Yeah. So if you need something, a thermal laser source, then you can really nicely use the CO2 laser. For the annealing, for the 3D printing, of course, and for the thermal welding, and also the CO laser. We have some in-house from Bicoherent. That's quite nice. We can also use it for more homogeneous heating into the material. This is something of these whole topics we had so far with the cutting and with the marking, because we don't want any heat over there. But if you think of something thermal processes, these laser sources are really a big deal, I would say. So we realized that for some projects for annealing and that kind of stuff, we really need these lasers.
This is the room for collaboration here, Wilfred, is that you have to give them challenges, and they are looking forward to help you. And I think on that you have been a star today. Francesca, do you think we should now go to our last speaker, because we are both in the LAMPAS community and we both love surface structuring? I think we are going to go to Forget. ForJet is a key company in EPIC, has made a big difference in the European ecosystem by bringing systems and processes for high-end laser-based processing. And today we talk about glass. Thank you very much for being with us. Thank you for being the last presenter of this epic meeting. The Chief Marketing Officer, Marc from ForJet, is in charge of sending us away the way we should. The floor and the attention of everyone goes to you, goes to the UK.
Thank you. So let me share my screen, share the presentation. Now that's funny, it's not coming up, isn't it? Ah, here it is. Okay, so thanks a lot for the introduction. And actually, maybe I can answer some of the questions that have been raised regarding usage of CO2 lasers and so on. ForJet is a machine integration company, and you can see what we're doing here. A few words to that. We are not only in the tire marking and laser cleaning business, but also in the glass processing business, including thin film photovoltaics, where we provide large laser edge deletion machines to delete the edges of the glass and to free them from the photovoltaic layers to provide a bonding surface and so on. And we also provide laser cutting based on filament cutting and laser patterning solutions to the market and different markets. And it's also, we were talking about, or we were seeing Guardian glass. We have those large machines to be able to pattern or cut the large pieces of glass. To support our business, we also have a micromachining job shop service located in Prutting near the nice Chiemsee, where we provide especially laser cutting job shop services. So if you want to bridge the time between the PO and the commissioning of the system, you can rely on our job shop services. We are located in Alsdorf near Aachen. We have subsidiaries in Atlanta and Shanghai, around 130 employees, including a large portion of R&D physicists and engineers. Now, we call it pearl cut technology, which is actually based on the filament cutting to cut glass and achieve the perfect edge, which is a perpendicular edge at the glass edge where the filaments have been formed. And this edge is too perfect in some cases because it doesn't have a face, a bevel at the edges. Anyhow, what we use is an ultra-short laser pulse. It's strongly focused, and the focus is elongated by means of special optical elements. A filament is forming in the glass, so we have a chain of little microfractures in the glass along the propagation of the laser beam, resulting in ultrafine bulk modifications of 1 to 3 micrometers in the glass. And this is a weakening, basically, of the glass. And you can then use a stage, as has been said already, use a stage to move this filament line along the cutting edge. Now the glass is weakened and you can mechanically break it, or you can use a CO2 laser to automatically separate the glass by heating it along the lines of filaments. And this CO2 laser creates a temperature gradient transverse to the cutting vector, resulting in tensile stress, and then the glass separates automatically. This doesn't work for every type of glass. You need some value of coefficient of temperature expansion to make it work. The solutions that we provide are called pearls, according to the pearl cut technology. And you can see on the upper right, it's basically a system that can be scaled in size based on a table where the glass is fixed to. And then the table moves underneath the laser beam, and the stage moves the laser head across the surface of the glass. And by using both motions synchronically, you can introduce any cut line into the glass. We can integrate into those systems different type of laser sources and different types of filamenting optics. We have heard about a few bezel beams and special optics we are using from Coherent, for instance. We are open. We, of course, rely on products, and products need to be standardized to some extent. So we try to keep our suppliers in a small number. The Pearl is actually ideally suited to support the backend mother glass approach in smart window manufacturing. Smart windows are those switchable windows where you can apply a voltage to the glass and you get a changing of the transparency state going from light to dark and vice versa. And those windows can be cut, and also in the mother glass approach, meaning you get a very large piece of glass which you have to cut into small products. It can also be used to process ultra thin glass going down to 30 microns and cut thick glass applications in architectural windows. And as I said, it's the perfect edge that you receive with a very low surface roughness to get a high edge strength and a very accurate contour. Now let's come to the patterning. Most windows today contain some kind of coating. Low E coatings or active coatings like in smart windows, and usually those coatings need to be patterned in some way to achieve, for instance, a bandwidth filter for mobile transmission. If you're riding on train, you would like to take your cell phone and talk to your friends outside, and the reception is bad because there's a coating, silver-based coating on the compartment window, shielding the glass. And when you structure this coating, then you can achieve a bandpath filter. This has to be done in a fast way and in a flexible way because you don't have just one product size and just one product. So what you have to apply is some intelligent way to get more beams on the substrate at the same time and guide each of those beams at very high speed. And that's what you can see on this picture. 5 beams in parallel based on laser scanning methods. But again, here we are facing different requirements from the industry. On the one hand, we are facing thick glass or thin glass, or we are facing the requirement that the footprint needs to be small. And if you have a large piece of glass and you have a portal system, like here on the upper left side, then this needs to be twice as long as the glass is long, and that will increase the footprint. If you have a gantry system like this, you can decrease the footprint. There you have the x-axis being mounted on the y-axis and moving across the glass. For each of those different requirements, we provide a solution, whether it's very thin glass, there the Topaz LS is the optimal one. If you have photovoltaic glasses, this Topaz LSGS is the optimal one, especially if a glass size patterning is asked for, which is usually more efficient and provides a high resolution compared to the layer side structuring. And then we also have a Topaz 3D, which is, as you can see here, made for windshield patterning. Coatings on windshields for heated coated glass, for instance. The heart of the system, as you can see in the video, is always a scanning on the fly system. So we have a combined motion between the scanner mirrors and the axis moving the complete scanning head or heads, and you have 5 multiple heads working in parallel here. This provides a much higher process speed, provides almost no stitching error. In this specific configuration, we achieve a resolution, patterning resolution of below 10 microns. So it's economical, whether it's in smart window manufacturing, building integrated PV, or flat transportation glass applications. Now to finalize my presentation, we heard about this hydrophilic glass. And what you can see here is a glass that has been processed by the laser. And you can see that we can provide a hydrophilic characteristic on the glass. And on the left side, when I get my pointer back, here it is. You can see it that it's also, yeah, here it starts, providing structures that can, oh wow. Yeah, it seems to be overloaded here, my system. Usually you should see something. Here it goes. And you can see that it's also provided with guiding structures. Yeah, so much for my presentation, and I'm happy to answer any questions and also to engage in some some discussions later on, maybe afterwards or later on during the next days. Thank you very much.
Thank you very much, Marc, for a great presentation. If you want, you can, of course, give us the presentation and we'll share it because those videos are really fascinating. I've seen them myself and they are really, truly epic. I think we have a lot of room for cooperation with you, so let's go through it. First question is from Arseny, from WaveOptics.
Thank you, Marc. Very interesting presentation. Just wanted to check what kind of sidewall roughness can we expect from the laser filament cutting? If you could give some numbers.
Yeah, it's around 1 micron.
But 1 micron means below 1 micron, above 1 micron.
Yeah, it depends a little on the glass. So I would rather make some trials with your glass to answer that question.
Because the reason I'm asking for our optical devices, there is a difference in those numbers.
Yeah.
And if it is like 300 nanometers and 1 micron, those are different numbers for us. Thank you.
Yeah, you're welcome.
The next question comes from Optoprim. They ask in YouTube, so I'm going to read it. And this is a good question, Marc. They're wondering about process control monitoring. What tools do you use for the process control?
Process control monitoring in terms of looking at the process zone, is that the question?
Yes,
and,
I mean, at the end of the day, you are processing the glass and you want to make sure that they satisfy certain quality. What kind of cameras do you use for that? Near infrared, do you go to the S-WIR, M-WIR band?
Yeah, we don't use any specific process monitoring. We have done that for the rare side ablative processing, where we looked through the processing optics, but we haven't done this for these processes. So actually, we take all the measures that we don't have to do that. You know, we have a height control in an inline closed feedback loop to really check the height or the distance between the processing head and the glass surface and so on. So that's what we do, and we do
Next
the laser.
Question.
Yeah, okay.
Next question comes from Switzerland.
Yes.
Posalux, and they ask in YouTube, even though we have people in the Zoom room, they ask in YouTube, what is the typical thickness of the glass that you normally work with?
30 microns to 8 millimeters.
30 microns to, okay. And we go now to biomimetic. Andreas has something on his mind for collaborating. Andreas, what's on your mind?
Hello, I would like to ask what are the optical properties after the treatment for the hydrophilic glass? And does the glass stay hydrophilic? Or what is the stability of the hydrophilicity?
Yeah, it stays hydrophilic. And the optical properties, you may have seen it, it's not transparent anymore.
Okay, that's great.
Marc, has been a great meeting. There's going to be many people who want to collaborate with you. You and all the rest, just remember that you have to stay if you want to have the one-to-one meeting. So you have to stay at the meeting. For me, I learned a lot today. So first of all, the whole meeting was about learning about potential end-user requirements. And we had two big challenges. One was coming from applied materials. And they gave us a set of specifications for them to find them partners. And that's gold for Francesca. That's why she was so happy during the meeting, because she's going to find what are the key companies who can offer this. The second one was from WaveOptics. I love this because they really are a company who's making a huge difference in the ecosystem. Helping them is helping Epic. It's helping me a little bit. So we need to help WaveOptics keeping being revolutionizing the waveguides in glass. But also we heard today about what are the main challenges in glass processing. It looks to me, after everybody talking, that is about the high numerical aperture, the high fluence being spot that we need, that typically has heard from you 1-2 micrometers, and actually having a scanning solution, which I think on the meeting Forget was fantastic on this. Marc, you actually told us about the scanning on the fly to increasing the throughput. We talked also quite a bit about reflective versus DOEs, versus diffractive optics, and it was quite interesting to at least have an initial hint of where to go and where his industry goes. I love what Kyle Labs has done with the Zentrum Hannover. I also love what the companies like Holo are doing as well. We have to find out mapping a bit better, and this Francesca is our expert, mapping a bit better what technology goes where. Plastic and glass bonding is a big challenge. We don't really have a solution, but many of you have actually hinted a bit of potential room for cooperation. And hydrophobic and hydrophilic sections, the idea of having a hydrophilic glass with hydrophilic holes. That's something that I really look very, very interesting. If I had to choose what is the big breakthrough, the room temperature bonding of Primoceler. Ville is a success story for this ecosystem. I really cannot believe how much we enjoy and how much we learn and how much we can collaborate in 2 hours. It's about being efficient. At the end of the day, all we want is to make sure that all of you find partners. So please do not forget that you have to follow up on the connections that we made today. Stay in the meeting if you want to have one-on-one connections. And of course, do not forget that if you want to get in touch with any of the participants, all you have to do is send me an email, hosted.board@epicdataso.com, and I will make that introduction. On behalf of the EPIC team, who is now the team that is the largest photonic association in the world, we would like to thank all of you for your attention, for your epic passion, and for keep giving us the energies and giving us the biggest smile that we have after such an epic meeting. Until the next time, keep being epic. Bye-bye.